So far I told you what this algebra UQG is. Well, that's here I recall the presentation of that algebra. And the next goal is to make it into a Hopf algebra. That's what's going to ensure us, as Chris explained, that if, well, let me call it A for the moment, that A mod, namely the category of A modules, is a tensor category. So far, there's nothing that tells us that it's a tensor category if you just give an algebra like that. So we need a coproduct that goes from A to A tensor A, a counit that goes from A to the ground field, which, well, is not C, it's C adjoint Q. But if you take Q to be a particular number, then it becomes again C. It depends how you interpret these relations. And an antipode so let's recall, these are algebra homomorphisms, and that one is an algebra anti-homomorphism. S of A times B is S of B times S of A. Well, they're homomorphisms or anti-homomorphisms. In both cases, it's enough to give them on generators, because if you know it on a generator, you can deduce it on a product of generators. And everything is a combination, linear combination of products of the generators, AI, Fi, and Ki. So let me just give you the formulas. Coproduct of the Ki's is easy. Coproduct of EI is EI tensor Ki plus 1 tensor EI. And a similar formula for Fi, except that this time the factor K appears on the other side. And to the power minus 1. Okay. We have the coproduct is 1 on Ki, 0 on EI, similarly 0 on Fi, and then finally I need to give you the antipode. Here you get an inverse. Antipode of EI is minus EI times Ki inverse. And this is Ki times Fi, again with a minus sign. Very good. So one thing that's fairly easy to check is that if you set q equals to 1, and also secretly recall that ki was q to the di hi, if you set q equals to 1, you're also putting ki equals to 1, because it's 1 to some power. So q equals to 1, then you recover the usual Hopf algebra structure on the universal enveloping algebra of a Lie algebra. So delta of a Lie algebra element is that element tensor 1 plus 1 tensor that element. And epsilon of a Lie algebra element is 0. And the antipode of a Lie algebra element is minus that Lie algebra element. Yes?
How do you get delta of h?
Delta of h is not apparent in these formulas because we've decided not to work with the h's. But actually, the h's in the case, the Cartan subalgebra, is the only part that we're not deforming. So if you had h in the game, its delta would not change. It would be delta of h is h tensor 1 plus 1 tensor h. Okay. So now there's a lot to check. I mean, I'm claiming this defines a Hopf algebra, but it's not at all obvious that it does. It's not. I mean, I wrote down a bunch of formulas. It doesn't mean that they make sense. So let's make a list of things that need to be checked. So we need to check that do these define homomorphisms? Well, in the case of S anti-homomorphism. In other words, do they respect these relations? So that's the question of, is this well defined? Second thing that needs to be checked is that the antipode is a coalgebra anti-homomorphism. And then there's the Hopf algebra. Then there's the relation that says this is an antipode, which is, well, if I call M the multiplication on A, then it's M composed with S tensor 1 composed with delta should be equal to M composed with 1 tensor S composed with delta should be equal to, first do the co-unit and then do the unit. So there's a lot to check. And I don't feel like going and doing all these verifications because it's actually quite a massive amount of verifications. But I want to show you one of each kind, just so that you get a feeling of what's going on. Okay, so an example of one. I'm going to check this second relation. The first relation is too easy. I'm going to check that delta is compatible with this first relation. So let's do it. So delta is by definition an algebra homomorphism, and therefore that is the same as delta of ki times delta of ej times delta of ki inverse. So that's ki tensor ki, all that times ej tensor kj plus 1 tensor ej, all that times ki tensor ki inverse. Well, let's work out what this is. That's an elementary tensor that has sum of two things. That's one thing. So you get two terms, and the terms look as follows. Ki ej ki inverse tensor kj plus 1 tensor ki ej ki inverse. You just multiply all the left-hand sides and all the right-hand sides and put them here and there. So for example, this kj is kj times kj inverse. Okay, now we're allowed to use our relation to replace this by q to the inner product of the simple roots, alpha I, alpha j, times ej, this one remains, kj, plus, and the same factor will come out here, so let me just put it in front, 1 tensor ej. Well, that happens to be equal to delta of this guy. So we've checked that delta preserves that second relation. It sends the left-hand side and the right-hand side to the same thing. Good. I mean, it's fairly straightforward. So let's check an instance of 2. So I will check this relation on the element ei. I also have to check it on ki. On ki, it's very simple. On ei, it becomes as follows. So that's delta of minus ei ki inverse, which is, by definition, minus ei tensor ki plus 1 tensor ei, all that times ki tensor ki inverse. When I apply delta to this and to that, that's what I get. Well, let's do the multiplication. We get minus ei ki inverse tensor 1 minus ki inverse tensor ei ki inverse. And then we can recognize that as being twice the antipode applied to the expression well, this is ei, but let me put this one there and that one on the other side. So it's ki tensor, and that's the antipode of ei. And this is, that's the antipode of ei, and that's just the antipode of 1. Let's see. Was that a good idea to do it like that? Why did I do it like that? I did it like that because I wanted to be able to see right away that this is exactly that in the opposite order, and that is exactly the other in the opposite order. So this is exactly S tensor S composed with delta op applied to EI. So again, rather straightforward. Let's do 3. So 3 is a little bit different than the other ones in the sense that it's not clear a priori that 3 can be, that it's enough to check 3 just on generators. I mean, the rest, I mean, this is an algebra anti-homomorphism, that's an algebra homomorphism, that's an algebra homomorphism, that's an algebra anti-homomorphism. And to check that 2 such anti-homomorphisms are equal, it's enough to check it on generators. And then you get the other thing for free. But if you look at that, well, that is an algebra homomorphism, that's an algebra anti-homomorphism. The multiplication is not an algebra homomorphism. And so a priori, even if I went and checked it for EI, KI, FI, it's not clear that I've checked it for everything. So rather than checking it for those generators, I'll give you the argument that says that it's enough to check it on generators. So suppose I have this equation for an element, let's call it the element little a, and the relation, so here I put the antipode, so that's the relation. And then I have another element, b, and the same relation holds for b. I want to know that do I get the same for the product? So that's what we want to show. And I claim that this is a formal consequence of that for A and the corresponding thing for B. Let me take some space and do it. Okay, so A, B, here, antipode, that's the same thing. Well, here I have product and then coproduct that can be replaced by doing them in the opposite order. Antipode. The antipode can be passed across this multiplication, and then the thing goes in the other direction. Before doing that, let me rewrite that in a slightly different way. So I really haven't done anything in this. So from here to here, nothing happened. I just moved things around. But now I can rewrite this using the relation for the fact that the antipode is an anti-homomorphism. So we get two antipodes, one here, and one here. Very good. Now, this is this was a product. Here I have a product, and a product. by associativity, you can decide in which order I do them. So I can rewrite it as this, and here this is like two products happening simultaneously. That's the same thing as well, now I use my relation for A. I use that. This is a product with a unit, so that can be removed. And I'm left with the same picture for B. And we'll have A, B, and that. And then this is the same thing as that, because that's, well, if you read it the other way around, what you're doing is you're taking, sorry, what do I want to read it? This is the product, okay, the product, the co-unit is an algebra homomorphism, and therefore the co-unit on A times B is the co-unit of A times the co-unit of B. So this is the same thing as okay, so that shows that it's enough to check 3 on generators. I'll leave it like that. Okay, so that's a Hopf algebra. And now that we have a co-multiplication in particular, it makes sense to talk about tensor product of representations. So let me do it in a simple case of SL2 to just see exactly what this tensor product of representations is. So this is SL2, sorry, UQSL2. This axis here is the weight. And if I take the product of the 3-dimensional and the 5-dimensional representation, I get something 15-dimensional. Like this, and the weight spaces are of dimension 1, 2, 3, 3, 3, 2, 1. This is really, you should think of it as being a rectangle that has been squished. So what are the raising operators for this representation? Well, they go like that. And if I had just a tensor product of 2 Lie algebra representations for SL2, what I would put is 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, and then the interior also 1, 2, 3, 4, and then 1, 2, 1, 2, 1, 2. Okay, that's not the way the element E acts now. Now it acts by quantum numbers. So we put quantum 1, quantum 2, and so on. And again, we're not quite done, because here, this is the picture that we would get if the coproduct was E tensor 1 plus 1 tensor E. We need to do E tensor K. So when I do E on the factor, I should simultaneously be doing K on that factor. So E on the three-dimensional representation, that's this 1 and this 2, and it needs to be modified by K on this five-dimensional representation, which is, well, here it's Q to the 0, here it's Q to the minus 2, and here it's Q to the minus 4. So I get a prefactor of Q to the minus 4. On this row, I get a prefactor of Q to the minus 2. Here there's no prefactor. Here there's a Q squared prefactor. And here there's a Q to the 4th. So I'm not going to fill in the whole thing, but you get the idea. And when Q is not a root of unity, I mean, okay, you can then ask the question, how does that decompose into the representation, into the irreducible pieces?
Could you say what are the arrows that when you have two arrows that come from one point?
Sorry. The dots are basis vectors, and the arrows say where the dots go. So this basis vector goes to that basis vector times this factor plus that basis vector times that factor. So this is a notation for sending basis vectors to linear combinations of other basis vectors. This basis vector goes to 0 because there's no arrows going out of it. So if Q is not a root of unity, then this decomposes in the way that you expect. Namely, there is one copy of the 7-dimensional representation, direct sum with a copy of the 5-dimensional representation, direct sum, a copy of the 3-dimensional representation. And the way you can convince yourself that that's the case is that that's the only way of getting weight multiplicities 1, 2, 3, 3, 3, 2, 1. If you try to make a combination of the weight multiplicities of the irreducible representations for SL2 so that you get 1, 2, 3, 3, 3, 2, 1, that's the only way of doing it. So there is a way of making a change of basis to go from here to there. It's kind of not obvious. For example, this vector here, well, what is it? It has to be this vector plus Q to the minus 4 times that vector. Because that's what you get if you apply E to this guy. And then if you apply E twice, you get this, and so on. But let me put a question mark here, which is that, is it really the case that this remains so also when Q is a root of unity? And I'm going to argue that then something funny happens. So the answer is, well, okay, let me give you the answer to the question. The answer to the question is yes, it decomposes like that when Q is not a root of unity, and when Q is a root of unity, depending on what root of unity, then other things happen. And it depends on which root of unity you're looking at. So let me pick a root of unity such that something interesting happens, and let me show you what happens. So I'll take q squared to be of order 5. The q is, in this whole story, I'm always taking q to be an even root of unity. And this is somehow related to the fact that I defined the quantum number n to be, well, let me get an example. Quantum number 4 is q to the minus 3 plus q to the minus 1 plus q third. The exponents of q jump by 2, and somehow this reflects into the fact that I want to take q squared to be a given root of unity. So q is always of even order. In part of the literature on quantum groups, people use a different definition where they put exponents that are half integers. And then you don't have this funny thing. But so, well, let's look at the 7-dimensional module and see what it looks like when q squared is of order 5. So it actually doesn't change. This is what it looked before, and it continues to look the same. When q squared is of order 5, except that quantum number 5, when q squared is of order 5, oh, I took a bad example. I should have taken quantum number 5. Here, let me is minus 4, minus 2, when q squared is of order 5, you can check. This sum is a sum of 5 points on the unit circle that are completely symmetrically placed, and the sum is 0. So this raising operator that's here, well, it just sends this vector to quantum 5 times that vector, but quantum 5 is 0, so I don't write it. And then we have the lowering operators that do the same thing. And the operator ki does, well, there's only one k here. The operator k does what it did before. So here it's times 1, here it's times q squared, here it's times q to the 4th, here it's times q to the 6th, times q to the minus 6. So that doesn't change. So this is what this module looks like. And let me now argue that it's impossible for this representation to break as a direct sum of this, and that guy. The reason is that the 3-dimensional representation is self-dual. Recall that we have a notion of dual here. That's what the antipode does. This is self-dual, and that's also self-dual. Therefore, you expect the product to be self-dual. Well, that is self-dual, but if I take the dual of this guy, okay, you need to work out the definition of dual, what you will see is that you get a similar kind of picture, but where you have arrows going out from these points to those points. And so this thing is not self-dual. And because it's not self-dual, it's not possible for this to have this decomposition. Let me give you another argument that shows that it's impossible. let's look at the operator E viewed as an operator from this three-dimensional vector space to that two-dimensional vector space. So it's an operator that's given, well, by a given 3 by 2 matrix, and I wrote down some of the entries of that matrix. What does that matrix look like? Roughly, it looks like this. So it's 3 by 2, and the first guy goes to the first guy, so there's an entry here and nothing there. This guy goes to linear combination of the two, and this goes there. So let's see what are the actual constants. This is quantum 3. That one down there is q to the 4th quantum 1. Well, that's just q to the 4th. What is this? This is q squared times quantum 2. And that one there, finally, is quantum 4. Anyways, that's this matrix. One can compute the dimension of the kernel of that matrix. And one can check that this dimension is equal to 1. These are actually all invertible numbers, even when q is a root of unity of that order. These are all invertible numbers, so by doing a change of basis, if you only care about the dimension of the kernel, you may as well replace it by the matrix 1, 1, 0, 0, 1, 1. And then you can easily compute that the only element in the kernel is the vector 1 minus 1, 1. But if I had this direct sum decomposition, I would have two vectors in the kernel. Namely, that one on the top, that's in the kernel, it goes to nothing. And that one down here, it's in the kernel, because here it's in the kernel of E. So that's the second reason why it's impossible to have that. So, okay, so how does it decompose if it doesn't decompose as a direct sum? Well, let me give you the answer. This 5-dimensional module, this 5-dimensional representation doesn't change. It remains as it is. That one is fine. And it's this 7-dimensional and that 3-dimensional together, well, they form a 10-dimensional thing that doesn't look like that. And what that 10-dimensional thing actually looks like is as follows. So we have raising operators, which I draw in red, that go as follows. Lowering operators that I draw in yellow. You guys don't see that it's yellow. And actually, I didn't quite draw everything here. There's also contributions, like if I do a raising operator on this one, I get this one plus a little bit of that one. And if I do a lowering operation on this one, I get this one plus a little bit of that one. But I won't write it down in the picture because that's not... This is a good thing to keep in mind, sort of. So what we see is that this guy here appears as a submodule of that. If I look at the top, this is a submodule. But this other piece here, the quotient, doesn't split. It's not a direct sum of a module of the submodule and a complement. There's a filtration. There's a submodule and a quotient. This is the submodule, that's the quotient. Yeah?
If you were omitting some part of a raising operator being a sum.
Yeah.
The one on the top of the submodule now.
Yeah, it's still a submodule. The arrows go up.
Oh, they only go up.
They only go up.
There's none from the top coming down.
Correct. So these arrows that I didn't draw are not interfering with the fact that this is a submodule. So let me tell you what these kind of V's are called. These are called tilting modules. And that's an instance of a tilting module. There is a general definition of what a tilting module is that works for arbitrary quantum group. And, well, that's the SL2 version of tilting modules. So let me give you a definition of what tilting modules are. Okay. So this was examples in SL2. Now I go back to the general theory. I give you some definitions. And at the end, I will have a definition of a tilting module. So okay, modules for UQG. First of all, we have the Verma modules. The definition is the same as the Verma modules before, and these are the guys that would start here and continue all the way and never stop. Then we have the quotients of the Verma modules. So let me call them W lambda, and this is the Verma module modulo the span of these smaller Verma modules So that would be, we have the Verma module that starts here, and then we mod out the Verma module that starts there, that sort of lives in it. Before I called these L lambda, and now I'm switching to call them W lambda. These are called Weil modules. And there's a reason why I do that change in terminology. It's because L sub lambda, well, it's a standard notation in the field to call L sub lambda irreducible modules. And these things are no longer irreducible. I mean, this is an example of a Weil module. So it's no longer the case that I divide by everything that's not able to come back to the highest weight vector via means of raising operator. I just divide by the things that I was used to dividing by in the classical case, and I don't divide by the new things that I could divide by. So this is not an irreducible thing in general. It might be when, I mean, this three-dimensional Weil module is irreducible, but in general it's not. And then we have the duals of Weil modules. They're called dual Weil modules, and they're the same as the Weil modules when W lambda is irreducible, and they're different when W lambda is not irreducible, as I explained before. And then there's the definition of a tilting module, and that's a somewhat abstract definition. So a tilting module is a module, let me call it T, that admits a filtration whose associated graded pieces, so one piece of the filtration modulo, the one just below, are Weil modules. So that's what we saw here. Like there's a submodule, which is the one on the top. That's a Weil module. And then there's the quotient, which is the one on the bottom. That's also a Weil module. I'm not done with the definition. And that also, well, and that admits another filtration whose associated graded are dual Weil modules. So Weil modules are things that are not self-dual, but tilting modules is a self-dual notion. In order to be, you're a tilting module if and only if your dual is a tilting module. So let me show you in this example what these two filtrations are. Okay, so I will redraw quickly that picture. Actually, I'll do it twice. That's once. That's twice. I draw the relevant arrows. So the arrows go up. Here we have arrows going both left and right. So this is an abbreviation of that picture. Well, what is the filtration? So here is the Weil filtration. That's the submodule. And the next step in the filtration is the whole thing. And the quotient is that three-dimensional guy. And the dual Weil filtration has this as a submodule. And did I draw it right? One moment. That's not a submodule. In order to be a submodule, you need to have no arrows going out of your thing. You need to remain inside regardless what you do. This is a submodule. And then the next step in the filtration is the whole thing. And, well, this piece is the three-dimensional Weil module, which is also the three-dimensional dual Weil module. And that seven-dimensional guy is the dual Weil module. It has these arrows going out instead of having these arrows going in. So that's an abstract definition. And then there are some structure theorems about tilting modules that say that any tilting module, I mean, this is, here I haven't defined any kind of indecomposable tilting modules. Any tilting module, I mean, if I take a direct sum of two tilting modules, that's again a tilting module. But there's a theorem that says that any tilting module decomposes as a direct sum of certain indecomposable tilting modules called T lambda. And for example, this is an example of an indecomposable tilting module where lambda is this guy here. Lambda is the highest weight. In this example, the filtration has length 2. I have this tilting module has a filtration of length 2, and the dual filtration is then also of length 2. In general, these filtrations can have longer length and involve many pieces. Then there's another theorem, which is actually a hard theorem, which is that if you take a tensor product of tilting modules, the result is again a tilting module. So here I took the three-dimensional representation, the five-dimensional representations. 3 and 5 were numbers that are small enough relative to that choice so that those two guys are irreducible. So in particular, they're tilting modules. And then I took the tensor product, and I got this guy and that guy. And these are, again, tilting module and tilting module. Well, that's a general fact. If you start with tilting modules, tensor them together, you end up with tilting modules. But this is far from obvious. This is a difficult fact. It's a theorem. So then the question is, which pieces show up in this filtration, in this Weil filtration? An equivalent question is, if I look at Weil modules, like this one, which sub-Weil modules am I going to encounter as submodules in here? So here I have the 7-dimensional Weil module, and inside it, say it's a 3-dimensional Weil module. And these like 7 and 3 then are the same numbers as the ones here. Somehow it's... let me tell you what can happen in an SL3 example. So an example of type A2. And I won't really tell you why that happens, but I'll just give you a feeling of what happens. Okay, so this is the, let's see. I need to make sure that I draw these things a little bit in more straight lines, because the picture is going to become complicated later. Okay. So drawing a piece of triangular lattice. Very good. So this is the origin. I pick a point that I'll use as highest weight. So let's pick it here. So the weights of the Weil module are going to be contained in in the convex hull of these points. Okay. And if I do a reflection along some of these lines, I get some other things. And that indicate the smaller Weil modules that live in it. That's one. And then I can also do a reflection along this. Okay, so in this example, the orange Weil module, the big one, has a sub-Weil module, which is this red one, and then there's a further sub-Weil module, which is this purple one. Let me draw the raising and lowering operators a little bit on this picture so that you get a feeling of what's happening. So here we have lowering operators that go along this line. And here there's a gap. Once you're in here, you cannot exit. And conversely, if you raise from the bottom, you can enter this red submodule, but you cannot exit. And, well, same thing between the red and the purple if you were using lowering operators that go in that direction. So, okay, so what is this picture? There's the weight lattice, which I did not draw, which is a lattice that has spacing roughly this. So it's like a whole bunch of points. That's the weight lattice. I didn't draw it. So what is it that I did draw? I drew some walls that partition this plane into simplices. And the reflections along these walls form a group that is called the affine Weil group. So the Weil group is the group generated by reflections along those three. And then there is a bigger group, which is our infinite group, that's generated by reflections along all these lines. When we were talking about Verma modules and the submodules that sit in it, we learned that inside M lambda, I have lots of M sub Weil group action on lambda. Well, now you have the same story, except you have the affine Weil group that plays a role. So inside W lambda, there's lots of W sub element of the affine Weil group acting on lambda. There's a parameter in this story, which is which order Q square has. And that parameter affects the size, the place where you put this extra reflection. So if you have Q square of very big order, this reflection is going to be very far away, and W lambda, if lambda isn't that big, is going to be reducible. You're going to see nothing. You need to have lambda, which is bigger in some qualitative sense than the order of Q. Okay, so I guess that's all I wanted to say. Thank you.